This is section 7.6a, linear programming. In this section, we're going to apply what we learned in the last section about systems of linear inequalities, because linear programming involves systems of linear inequalities. So, linear programming is a strategy for finding the optimum value, either maximum or minimum, of a linear function that is subject to certain constraints. Now, you can write that down if you want. It's okay if that doesn't make sense to you yet, because I think with the examples it will become much more clear. Why is it called programming? Well, programming is a way of planning. I know that we don't usually use program with that meaning, but that's another meaning for programming, is planning. And so linear programming is used in business planning to either minimize costs or maximize profits. Now, the constraints or restrictions are stated as a system of linear inequalities. So we're going to look at a specific series of constraints. For example, we want to find the maximum value of z given z equals 3x plus 2y and these constraints. 2x plus 5y is less than or equal to 25. 3x plus 2y is less than or equal to 21. X is greater than or equal to 0. Y is greater than or equal to 0. 3x plus 2y, for example, could be a function for profit of a certain business, and we're trying to find the maximum profit, z. And that maximum profit is subject to certain constraints. They could be restraints of cost, how much you are able to spend. They could also be constraints of time, how much time you can spend, or constraints of materials. So there are different constraints to which profits or cost can be subjected to. And we always want to maximize our profits and minimize our costs. Now, again, what we've seen on this screen might seem a little bit foreign. You probably haven't done linear programming before. That's okay. The best way to learn, as usual, is by example. And then at the end of this section, when we get to the next lesson, we're going to talk about concrete applications of linear programming. So for now, it's enough to know that linear programming is a way of optimizing, of finding a maximum or a minimum of something, usually a maximum profit or a minimum cost of a linear function, and that linear function usually represents the cost or the profit. And these constraints or restrictions are what the system of inequalities provide. All right, so that system of inequalities that we see here, 2x plus 5y is less than or equal to 25, etc., that system of inequalities defines the restrictions or constraints for this linear programming problem. Okay, now we're going to specifically look at how we solve this problem. And it's similar to what we did in the last section. In 7.5, we solved systems of linear inequalities graphically. So we're going to be using that method as well for linear programming. This z function is called the objective function. It's always a linear function, and you can see that we could easily put this in y equals mx plus b form. It's a linear function as opposed to a quadratic or cubic function. The objective function is always a linear function. And our inequalities are our constraints. So we are going to use the same system that I showed you on the last screen, and we're going to work through it step by step. The system of linear inequalities determines a set of feasible solutions. This would be equivalent to the shaded common region of what we did in the last section. The graph of this set is the feasible region. So for this specific example, graph the feasible region determined by the system of constraints, then label the vertices. Okay, so you know what to do first. This is really similar to what we did in the last section. You should be able to graph these inequalities, shade the appropriate common region. So pause the video, do that, and then resume when you have the inequalities shaded. So going through the graphing now, we can graph the easiest ones first. X is greater than or equal to 0, y is greater than or equal to 0, and you can see that I have both of those inequalities graphed in the light blue color. And since it's greater than for both, then I would want to shade to the right of the vertical line and above the horizontal line. But as we did in the last section, we're going to hold back on the shading until we can see what the common region would be. The graph of 2x plus 5y is less than or equal to 25 looks like this. And you can, of course, prove that to yourself if you were not able to graph that on your own. But this is just a simple linear function that can be graphed. Usually it's best to put it in y equals mx plus b form. And 3x plus 2y is less than or equal to 21 looks like this. That's graphed in red. And our feasible region is that light blue shaded area. And that is the shaded area that's common to all four of these linear inequalities. Therefore, any ordered pair within the feasible region is a valid solution to this system. Now, our vertices, we find those in the same exact way that we used for the last section. For every particular vertex, we simply create a subsystem and just turn them into equations. Okay, like for 0, 0 there on the lower left portion of the feasible region. Well, in that case, I'm just looking at two specific inequalities. X is greater than or equal to 0, y is greater than or equal to 0. And I simply get rid of the inequality signs and make them equal. So x equals 0, y equals 0, those are my coordinates. And we don't need to go through the rest of the ordered pairs because it's the same exact method that I described in the last section. So we have our four vertices: 0, 0, 0, 5, 5, 3, 7, 0. Now continuing with the problem, up until now, what we've done on this specific example is similar to what we did in the last section. Okay, just graphing and finding vertices. Well, what makes this a linear programming problem is that the solution to what we're trying to optimize is at a vertex of the feasible region. Okay, so this should make clear now and during the rest of this section the whole point of finding vertices. So let's see how this works. We are going to maximize the value of z equals 2x plus 3y over the feasible region. What that means is, in this feasible region that's pictured, we have four vertices, and we know that any ordered pair that's within the feasible region will satisfy the system, but what we're trying to do is satisfy the system and maximize z at the same time. We want to achieve both objectives. So in linear programming, it's not enough just to graph a region. We're going to find a specific point, a specific ordered pair, at which I both satisfy the system of constraints, and I also maximize or minimize, depending on what we're trying to do, the objective function. So here the objective function is z equals 2x plus 3y. I want to see which x and y ordered pair are going to give me a maximum value for z. So what we do is we test each vertex by plugging in those x and y coordinates into the objective function, and we see which of those ordered pairs will yield the largest number for z. Alright, so starting with the vertex 0, 0, if I plug that into my objective function z equals 2x plus 3y, I get z equals 2 times 0 plus 3 times 0, and that equals 0. Now let's test the 0, 5 vertex. If I plug the ordered pair 0, 5 into the objective function z equals 2x plus 3y, I get z equals 2 times 0 plus 3 times 5, and that equals 15. Now I'm going to test another vertex, the 7, 0 vertex. If I plug the ordered pair 7, 0 into the objective function z equals 2x plus 3y, I get z equals 2 times 7 plus 3 times 0 equals 14. And finally, we'll test the 5, 3 ordered pair. And I see that if I plug in 5, 3 into the objective function, I get z equals 2 times 5 plus 3 times 3, and that equals 19. Well, 19 is bigger than 15, and bigger than 14, and bigger than 0, so that's the maximum value of z. The maximum value of z, which, of course, also satisfies the constraints. And so we have found the maximum value of z as 19, and this occurs at the point 5, 3, the vertex 5, 3, when x equals 5 and y equals 3. And thus we have finished together our first linear programming problem. Another example, find the maximum and minimum value of z equals x plus 3y subject to the constraints negative x plus 3y is less than or equal to 6, x plus 3y is greater than or equal to 6, and x plus y is less than or equal to 6. We have our constraints, we have our objective function. We want to find the maximum z and the minimum z. So our first step is to graph the feasible region. And when we do that, we can graph negative x plus 3y is less than or equal to 6. We can graph x plus 3y is greater than or equal to 6. And we can graph x plus y is less than or equal to 6. These are three lines which form the boundaries of these inequalities. And we shade the region that's common to all three of these inequalities, these three constraints. For negative x plus 3y less than or equal to 6, shown in black, we shade under it because it's less than. For x plus 3y greater or equal to 6, shown in red, we shade above it because it's greater than. And for x plus y less than or equal to 6, shown in blue, we shade to the left because it's less than. So we shade under the line. Next we find the vertices, and we can find the vertices in the way we have in the past. We get 0, 2, 3, 3, 6, 0. And in this case, you can really just read those off the graph. You don't even have to do it arithmetically. We can see pretty clearly on the graph that we can get those coordinates just from the Cartesian plane itself. Third step, we evaluate the objective function at each vertex, like what we did in the last example. We're going to use the objective function z equals x plus 3y, and we're going to test the value of the objective function for each vertex. When we do that, for the 0, 2 vertex, we get z equals 0 plus 3 times 2, and that equals 6. For the 6, 0 vertex, z equals 6 plus 3 times 0 equals 6. And for the 3, 3 vertex, z equals 3 plus 3 times 3 equals 12. And for all of those, you can see that we simply use the objective function z equals x plus 3y with the different ordered pairs. Now we can conclude that the maximum value of z is 12 because that is the highest z that we can get for this feasible region. We can also see that the minimum value of z is 6, and we got 6 for 2 of the vertices. And therefore, we can conclude that the maximum value z is 12 and occurs at the vertex 3, 3. The minimum value of z is 6 and occurs at both 0, 2 and 6, 0, and at every point along the line segment joining them. At every point along the line segment joining them. Because whatever point we plug in, if it's on that line segment, we're going to end up with the same z of 6. Now, what I'm going to show on this screen is something you don't need to take notes on. Just try to follow along. Because the only purpose of what we're doing on this screen is to clarify and illustrate. Now, you might actually find that it doesn't help you, it doesn't clarify. So if you find that, then just ignore what you see on this screen. But some students find this helpful. So again, you don't need to take notes on this specific screen. Just kind of watch and pay attention. So we can rewrite the objective function z equals x plus 3y, the one that we just saw. We can rewrite it in slope-intercept form, and we'll get y equals negative 1/3 x plus z over 3. Slope-intercept form is just y equals mx plus b form. That's what it's called. It's called slope-intercept form. And we can easily see that z equals x plus 3y can simply be rearranged to give us y equals negative 1/3 x plus z over 3. This equation represents a family of parallel lines, one for each value of z. Okay, so remember that the value of z can vary. And according to this slope-intercept form, when I change the value of z, I'm only going to be changing the y-intercept of the lines. So let's see what that will look like. This is the feasible region that we already saw on the last screen. And now let's test different values of z and see if we can recognize a pattern. If z equals 0, then y equals negative 1/3 x. And we can see that just by plugging in 0 into the slope-intercept form that we have above. And I have the equation of the line y equals negative 1/3 x with a y-intercept of 0. That's what this line looks like, obviously outside of the feasible region. If z equals 3, y equals negative 1/3 x plus 1. And I get that just by plugging in 3 for z in the slope-intercept form. Now, the choosing of these values, 0 and 3, is completely arbitrary, right? That's just at my discretion. But you could choose any values for z, and you'd get some kind of parallel line, because the objective function still has the same slope. The only thing we're changing is the y-intercept. Now, for z equals 6, y equals negative 1/3 x plus 2. That's what happens when we plug in 6 for z in the slope-intercept form, because 6 divided by 3 equals 2. So my y-intercept is 2, and I can see that this line intersects the feasible region not only at 1 or even 2 points, but at every point that's in that line segment which connects 0, 2 to 6, 0. For z equals 9, again I'm just choosing random values at different intervals. Well, plugging in z equals 9 for z, I get y equals negative 1/3 x plus 3. And I can see that this line does go through the feasible region, but it doesn't go through any vertex, and so it can't be a maximum or minimum value. Maximums and minimums only happen at the vertices. For z equals 12, I get y equals negative 1/3 x plus 4. And this line, which has the y-intercept of 4, this line does pass through a vertex, and so it can be a maximum or minimum. And given the value of z, 12, which is greater than any of the other z values, it must be our maximum. Z equals 15, just testing outside the region now, I get y equals negative 1/3 x plus 5. That is clearly outside of the feasible region, so I can throw that out. And the whole point of this is, again, just to clarify and illustrate. If you don't find it helpful, then just forget about it. But there are some students who do find it helpful to see this pattern of parallel lines. And you can think of it this way: as z increases through values 0, 3, 6, 9, 12, and 15, the corresponding line passes through the feasible region. Of course, we could have used a lot more values than just those. We could have done 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, etc. Just for the sake of time, we didn't do that. The point at which the family of lines, the family of parallel lines, first meets the feasible region gives the minimum value of z, and the point at which the family of lines leaves the feasible region gives the maximum. Alright, so this is just a pattern that might help you to understand linear programming. If you don't find it helpful, well, just remember that the maximum or minimum values in a linear programming problem must occur at one or more vertices. That's the key point. Another example: minimize z equals 3x minus y subject to x minus y is less than or equal to 1, x plus y is less than or equal to 5, x is greater than or equal to 0, and y is greater than or equal to 0. This is a linear programming problem. We have z equals 3x minus y as our objective function. We have 4 constraints, which is our system of linear inequalities. And you, for practice, should pause the video and try to do this problem on your own. You're trying to minimize. Okay, so you want to find the smallest possible value of z. And that smallest possible value, z, still has to satisfy the constraints. So pause the video, do this on your own, and resume when you have an answer. Alright, we're going to go through the solution to this linear programming problem now. We first graph the feasible region. I can start with our easy ones. X is greater than or equal to 0, y is greater than or equal to 0, and that looks like this. Of course, that would be shaded to the right of the vertical line and above the horizontal line, but we're going to save the shading for the end when we can shade the common region. We graph x minus y is less than or equal to 1. We graph x plus y is less than or equal to 5. And I shade the common region. That's what we see in blue here. My vertices 0, 0, 1, 0, 3, 2, 0, 5. And now I'm going to test each vertex because I want to see what each vertex gives me in terms of z. So for the vertex 0, 0, I get a z value of 0. For the vertex 1, 0, I get a z value of 3. For the vertex 3, 2, I get a z value of 7. For the vertex 0, 5, I get a z value of -5. Now, since we're trying to minimize, you can clearly see which is the smallest z value, and the smallest z value is -5. The minimum value of z is -5, and this occurs at 0, 5, the vertex 0, 5. Now, hopefully you were able to get that on your own, but if you weren't, don't worry about that, because you are going to see some other examples in this lesson and the next lesson, and of course we'll be able to do this together. Here's the classwork, page 558, numbers 1 through 15 odd.